Next, we will take a look at a differential equation that arises from population growth. And this is a really good example of observing a phenomenon in the real world and seeing how a differential equation naturally arises from what we see. And then it's an equation that we can solve, and we will work through the entire solution here. The idea is this. Think about population growth. The more people there are, the faster the population grows. And that's because the more people there are, the more people that there are reproducing. And it works not just for people, but for anything. If you have a bunch of rabbits in the forest, the more rabbits there are, then the more rabbits there are having baby rabbits. Or if you have bacteria that divide and grow, the more of them that are there, the more of them that are reproducing. So the rate of change of the population is proportional to the size of the population. And I'm going to write that down as a sentence here. The rate of change of P, and I'll use P for population. The rate of change of P is proportional to P. And that idea should make sense. That idea should make sense to you just based on your understanding of the real world. Now, this sentence is a mathematical statement. I can translate that directly into an equation. The rate of change of P, that's dp dt. How P changes with respect to time. dp dt is, that's equals, is proportional to P. That means it equals some constant times P. And there we have it, a differential equation. We see P and its derivative showing up. And P, of course, is a function of time. That's the population, which is changing over time. So we have this function and the derivative of the function showing up in the differential equation. And that's what makes it a differential equation. An equation in which the function, not just a variable, but the function and its derivative both show up in the equation. That is what a differential equation is. So note what the solution will be. Solving this differential equation means finding the function p of t that satisfies this equation. And this one's not too hard to solve if you know a little bit of calculus and how to deal with exponential and logarithmic functions. So here's the solution. We'll start with our differential equation. dp dt is equal to some constant times p. I'm going to rearrange this. I'm just going to algebraically move the pieces around to get this. 1 over p times dp is equal to k dt. And then I'm going to integrate both sides. So I integrate the left and integrate the right. And the integral of 1 over p right here, 1 over p dp, is just the natural log of p. And on the right side, I have the integral of k dt. That's just going to be kt plus c. Now remember, I'm trying to solve for p here. So to solve for p, I need to exponentiate with base e to get rid of this natural log right here. So I exponentiate both sides with the base e, and the left is just e to the power of ln of p, and on the right it's e to the kt plus c. All of that is now up in the exponent position. And I'm going to continue over here. And on the left, of course, e to the ln of p is just p. And on the right, e to the kt plus c can be written like this. E to the kt times e to the c. And if you don't see that, just remember your rules of exponents. Remember, a to the power of m times a to the power of n is a to the power of m plus n. So apply that concept in reverse, and you'll see that these two exponents here multiplied together is the same as an e with those exponents added, which is what we had down here. So it's just my rules of exponents that get me from here to here. Now note this, e to the c is a constant. So instead of just saying e to some constant, let's just call that c. Okay, so I'm going to write it like this. I'm going to write p is equal to some constant times e to the kt. Now I've found a function p, and that function will satisfy my original differential equation. So we have a solution here, but we don't know what c is yet. I'll show you how to do that next. Okay, it turns out for this equation, p equals c e to the kt, we can figure out what c is pretty easily by thinking about the population at the beginning when t equals 0. So we're going to let t equal 0 and see where that leads us. If t equals 0, then p is equal to c times e to the k times 0. And k times 0 is just 0. And e to the 0 is just 1. So that becomes 1. So p is equal to c when t is 0. So right at the beginning, p is equal to c. So c is the population at time 0. That's what c is. C is the initial population. And instead of calling it c, it makes sense to call it p0. And that little subscript 0 just typically means the population at time 0. So we could write our solution to the equation like this. P is equal to p0 times e to the kt, where p0 is the initial population. Now this constant k, we don't know it yet. We would need some more information to find k. K is a number that tells us how fast this particular population grows. And it would be different for different populations. The rabbits in the forest would have one value for k. The people on Earth would have another value for k. The bacteria in a dish would have another value for k. But it would be a number that's a constant for a given population. Now obviously populations don't grow exponentially forever. They would run out of room. The people on Earth would run out of room. There are limitations to population growth, natural limitations such as space and food supply and other things such as spread of disease. But in the absence of those things, population growth follows an exponential curve. This equation arises from our initial assumption that the population growth is proportional to the population. And that is the solution. That's p. It's a function of time, and that's the solution to our original differential equation.